In electronics manufacturing, defects don't usually announce themselves. They happen in milliseconds, far faster than human perception, and often long before anyone realizes a process has drifted out of control. By the time failures show up in tests, inspection, or worse, in the field, the root cause may be buried deep inside machine behavior that no one thought to question. Hi again, everyone. I'm Mike Conrad. In this episode of Reliability Matters, we're exploring a fundamental but often underestimated reality. Accuracy and force compliance are not just quality metrics, they are reliability enablers. When machines are assumed to be accurate instead of proven to be accurate, and when force is set but not verified, hidden variations creep in. That variation can translate directly into cracked components, misalignment, latent damage, and long-term reliability risks. My guest today is Michael Sivigny, SMT Productivity and Profit Strategist and owner and General Manager of CeTaQ Americas, a company that has spent decades doing what most factories don't, objectively measuring machine performance under real production conditions. Michael's work has repeatedly shown that even well-maintained, recently serviced equipment can operate outside of specification, quietly generating defects at high speed. In this conversation, we'll dig into how accuracy validation and force measurement expose problems traditional troubleshooting misses, why OEM calibration is no longer enough for today's miniaturized electronics, and how statistically sound measurement practices improve not only yield and uptime, but long-term product reliability. If you believe reliability starts long before functional tests, this is a conversation you won't want to miss. My conversation with Michael Sivigny begins right now. Stick around.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Hey, Michael, thanks for joining me. I'm glad you're here today.
Absolutely. Thanks, Mike. Appreciate you having me here.
Well, let's talk reliability, since that's the theme of the show. First of all, let's get into your company a little bit. Where'd that come from? What got you into that space? And what types of services do you provide?
Sure. Since CeTaQ GmbH started their business in Dresden, Germany in 1996, we have been offering the industry objective methodologies for checking machine capability. And all of that helps improve process and product reliability. In 2001, 5 or 6 years after these guys started their business, I started representing them here in the Americas territory. So that's how CeTaQ Americas got started, and the services we offer are on-site at the machine type of measurement services to understand what's happening with the equipment and trying to adjust the equipment with the data that we're collecting live in the machine. And it's a relatively quick cycle of adjusting, measuring, and then final validating what we've done to help them improve the machine performance.
So you're in the field. I mean, you're not a manufacturer of any sort. You're not providing equipment, or I should put that more in the form of a question rather than a statement. Are you also building equipment that customers can use for similar purposes, or are you a labor-oriented company?
We are doing both.
Okay.
And the services are on-site anywhere in the world with all of our colleagues. We're about 20 or 22 people large for the world. And going anywhere we need to go that needs our measurement. And the products that we're offering, we offer the service with our products also, but they're a bit dialed down for our service and transportation and such. But then we offer sale of products that are more aesthetically set up for in-factory use for customers to do their own measurements.
Excellent. You often say, if you don't measure, you don't know. In SMT manufacturing, what are the most common assumptions engineers make about machine accuracy that turn out to be wrong once actually measured?
Interesting. And yes, I say that often. I want to say that I coined the phrase because I want royalties if anyone else is using it.
Copyright Michael Sivigny.
No, but it's the full gamut. Most equipment users think it's highly sophisticated automation. Why does it need to be measured? But it was just calibrated, or they can't believe it was that far off, or they think fiducial recognition perhaps solves all the inaccuracies in the system. But while it's a tagline, the truth is it's true. When automation runs at near lightning speed these days, it's faster than any human can comprehend. And you need to have a special measurement technique to be able to see through that speed, through curves and data and analysis, to be able to understand, analyze, and then adjust to validate the performance.
You think AI is, first of all, my view on AI is it's totally revolutionary. It's more powerful than, we're just seeing the tip of the iceberg in terms of its impact on the world, positive and negative. But it's also overhyped, if that's even possible. Do you think that that AI will work itself into what you do in terms of the inspection of machines and ensuring accuracy, and maybe analyzing stored data that machines store but really don't do anything with?
It's true, and their SMT lines are data hogs. They are producing so much data. They need individual servers just to handle each machine. Data that's coming off AOI and SPI. That's a lot of stuff to analyze. So AI usage in those situations is going to be very important, just for the speed at which it can analyze the data and make recommendations. I do see it in our future as well, more in predictive analytics based on measurements that we've collected, understanding how every OEM's equipment performs and what the mean time before failure might be, or mean time before remeasurement of sorts. It would start to collect all that information, be able to analyze it, and then it will tell us when this machine is going to go out of spec and when to make a measurement to adjust. Definitely think it'll be in our future.
Yeah, I would think it would as well. Without naming names, we want to protect the guilty. Is it your experience that whether it's within stencil printers or pick and place machines or any other of the myriad of assembly equipment that your company will service or inspect, do you find that within one type of machine, all the various brands have their strong points and their weak points? It's analogous to, I'm kind of a motorhead. I love cars. And, it's long been said, never buy a first-year General Motors product because it's not done yet, right? And, or don't buy a GM car built on Friday, or whatever the case may be. Is there an equivalent? Do you have your little secret black book of, it's a Acme brand pick and place machine or an Acme brand stencil printer. Therefore, I know what to look for. You know what I'm saying? Or are they all pretty universal in terms of stable results?
So we are measuring everything in the SMT line. So laser marker, printer, dispenser, SPI, place of machine,
Ovens?
reflow oven, AOI.
Yeah.
Ovens does also, we can provide that type of service also. So we're measuring everything, collecting everything on everybody, and we're independent third party. So yes, I can't answer your question to who is the best or any of that. But when we haven't measured everybody that's in the industry. Of course, someday we would like to be in that situation, but we'll say that certain OEMs have a signature quality about them.
There you go. That's where I was going with it. And I'm not trying to throw any OEM under the bus, but that's one advantage in using a company like yours, where an OEM might be very experienced with widget brand A, and they don't know anything beyond that widget brand A. And the good thing about working with a company that's collecting data from widget brand A, B, C, D, E, and every other process down the line and up the line, I think it provides a broader interpretation of accuracy, and because some things caused by one machine might land and show on another machine subsequent to that, right? So, the process, the defect occurred at point A and showed up at point D. And by having that wider approach, analyzing all of the data, one basically expands the search, right? It's a larger field that you're searching in. Is that an accurate interpretation?
Sure. Yeah, you have to measure to have a baseline to understand how to improve, and everybody has their own specifications. Some OEMs may need help understanding their own specifications, but we've seen and tried to help along those lines, like testing machines at 3 Sigma versus 6 Sigma, and then what the standard deviations are for those given machines, and we try to educate the end users on all of that, so that they can understand themselves how to improve their machine performance. So we're trying to level the playing field, try to reduce the specmanship between OEMs, and give good advice for customers.
Why is it no longer sufficient to rely on OEM calibration alone for today's miniaturized, highly reliable electronics? So, someone may say, our calibration department did it. It's in spec. Check. Put an X in the box. Next. Why is that alone not sufficient anymore?
So through all of our measurements, we have time and time again found that even installing and measuring new equipment, brand new out of the box, and optimized and calibrated and internally measured, that those machines still fail our test when we go in to measure them. And that alone shows us that there is another level of performance above and beyond a calibration by the OEM that can bring the machine to its ultimate capability in terms of accuracy, force compliance, whatever. As electronics and technology continues to shrink, there's an expectation of reliability with any design. So modern assemblies, they're demanding some type of verification so that there is some comfort level with what the end product is going to perform like. So that's how it works.
From your experience, which causes more hidden reliability risk? Poor accuracy, poor force control, or interaction between the two, or other factors?
So there's poor accuracy can usually be seen, and perhaps AOI or SPI can correct that, or a CeTaQ intervention can correct that. But poor force control can result in damage that's not easily seen on the components or in the assembly. The most hidden reliability risk is at the intersection of both. And when you have a print offset that is in one direction and a component placement in the opposite direction, you have a very small intersection of a heel fillet, for example. And when that gets through reflow, if it actually gets that far, and through force, you're cratering pads perhaps with too much force. You're squashing solder paste out the sides of, out from under the component. There's a lot of things that can happen. What can happen also with force is that microfractures that can happen, and those are invisible to the inspection eye. And AOI or SPI, AOI is not going to pick those up unless they're gross. So
Right.
that's the risk of that.
Interesting. How does machine accuracy drift over time, and even on well-maintained equipment? And why is that drift often invisible to production teams?
Machines are built with tolerances, and even well-calibrated machines, they have they're going to drift. They're going to have backlash. They're going to need lubrication. If machines aren't properly maintained, you're going to see stuff happen faster, and that's how drift can go unnoticed if they're not calibrating regularly. I mean, we've seen some recent machines, even after our optimization, that 3 months later, for some reason, it goes out of whack again. So the frequency of measurement to understand and keep these machines in spec, it's wide ranging, but we know for sure that every year, at least 90% of those machines we test are failing again.
Wow.
So it's something that we know
Wow.
it's the statistics are showing that, and that's why it's important to keep regular measurements happening.
Can you explain the difference between machine capability and process capability, and why confusing the two leads to long-term quality issues?
They are separate, but absolutely connected. And machine capability is testing the machine in a controlled situation with low variation tools to assess the capability of the machine and its performance. It does not consider operator's environment, anything else. When you look at the process capability, you're looking at the machine plus the operator, plus the interactions, plus the materials, plus the environment. You could have good machine capability and bad process capability, and variables for materials and operators if they're not controlled well. So but you'll never have good process capability with bad machine capability, because the machine is adding too much variation in that case. So it's kind of establish the machine capability, make sure the machine is good, and then consider everything else around the process to understand that.
Yeah. In your accuracy validation studies, what types of defects tend to trace back directly to placement or printing accuracy rather than materials or design?
So in printing, the biggest is stroke-dependent offsets, and each stroke can have X, Y, and theta offsets in each stroke direction. So if you're trying to optimize a printer, you need to consider those two, all those variables. And for an operator, or a technician perhaps, who is trying to understand first article inspection and why there are offsets in any one of those stroke directions, and then looking at the assembly, the print alignment, and trying to assess how much theta rotation there is. And that's not an easy task. So there's a cost in terms of setup time and diagnosing that. And the idea with optimizing all these conditions is to prevent that type of stuff from happening. But offsets are big between printing and placement. Printing is the number one opportunity provider for defects at SMT. And if the print is not aligned for the placement, then you can get tombstoning, you can get other different defects that can cause issues down the line.
Earlier in my career as a manufacturer of equipment for this space, I was always amazed at the pick and place people, the major pick and place companies, because they would advertise component placement rates that were massive. And I would talk to end users, and I don't think I met anyone who was hitting the top speed, the top advertised speed. There was one particular brand, and I won't say who they are. that was just known for what I would view as very exaggerated claims. 120,000, CPH and all this stuff. And yeah, it probably is validated, but a very, very, very narrow, one type of part, with everything close together and, all that. But anyway, and that kind of, in that context, I'll ask this question. What risks do manufacturers take when they prioritize throughput over running machines in what you call, and I love this, if you're going to trademark another phrase, trademark this one too, maximum accuracy mode. So as opposed to CPH, maybe it's ACPH, right? Or CPH accurately, CPHA or whatever.
So IPC did a great job pulling together IPC 9850, and that's the characterization of placement machines. The committees and subcommittees that put that together helped set the playing field to test CPH, to test accuracy also. And we have adopted some of the gauge R&R aspects from that document into our own routines. But at least there's a way to test takt time, to test CPH, to use the same layout to be able to check those things. So that standard does exist for being able to compare one against another using the same type of tools. And CeTaQ can measure CeTaQ can measure the IPC boards to be able to help do that also if somebody is not able to produce purchase the kits from IPC. But anyways, that was part one of that. The part two is the maximum accuracy mode. That's the fully adjusted performance condition of the machine after calibration, after soft calibration with CeTaQ methodology that I refer to as maximum accuracy mode. So if they're not there at that maximum accuracy mode, then there's a sub level of performance that they're not, that this where they are if they're not getting the full impact. But when a line is fully optimized for quality, they get more efficiency because the machines are down less, they're dialed in, they work better. And increased efficiency contributes to more capacity through the line. More capacity results in more productivity over a specified period of time. And all that productivity and less rework helps with lower defects, creates compounding effect on profitability. So they risk not being as profitable as they could be with subpar performing machines and processes.
Yeah, sometimes the best move to speed up is to slow down, and measure. The old adage comes from like grandfathers. You can just see them saying that. Measure twice, cut once, right? So, it takes a little extra time to measure twice, but then again, how much time are you spending in all the downflow problems? That emerge from that.
Yep.
Why is statistical significance so critical when evaluating accuracy and force instead of relying on small sample checks or spot maintenance from time to time?
Well, statistical significance means measuring at least 30 of something. That's the very base of in statistics to have some idea of how a process is performing. So when we're looking at trying to test a machine, we look at all the functionality of that machine. It's the number of heads, the number of nozzles on each head, and then we design a layout that considers all the heads from the gantries and the placement rotations, and then repeat for a number of iterations. And maybe it's 700 components in a layout that gets placed by a machine. And then the power in our software is to break all that down into heads, angles, gantries, whatever it may be, and then even associations of 0 degree at head 1, 90 degrees at head 2, And then you have these offsets, these small associated offsets that can then be soft calibrated back into the machine to be able to really dial in that machine.
What are some of the common mistakes you see when manufacturers attempt to interpret capability data without a strong statistical foundation? And they're kind of doing it blind, right?
Well, it would be kind of blind, yes. If you're not using a statistically significant sample size, at this perfect example, OEM wants to design a new machine. They want to market this new machine at a certain specification. That's great. Technically, they should have 30 machines off the line measured with the same process to gain some statistical understanding about how 30 machines are coming off that line before they publish their specification. Is that happening? I'm sure it's not happening in every OEM situation, and not every OEM is in business with us. Although we'd love them to be, and can offer them that, but that's what it is. You need to have some statistical significance with the number of measurements you're making to be able to have confidence in where things are going.
And continuing down the OEM subject, in your case studies, you've uncovered problems even after OEM service visits. Why do traditional troubleshooting approaches often miss these types of issues? They're just looking in the wrong place? They checking a box? I mean, what's the story there?
Yep. Well, there's OEM calibrations are not considering all functional aspects of the machine. For instance, I mentioned the stroke-dependent offsets. There's not one printer OEM, I'm going to go out on a limb here and say this. There's not one printer OEM in the market that is calibrating their machine with print-dependent offsets in their machine calibration. It's just not there. And CeTaQ has a new tool to be able to help do that. But nonetheless, the fact that calibration of the OEM tools, they're just not they're not able to bring the machine to its ultimate capacity, like I mentioned earlier.
For manufacturers just beginning this journey, where should they start? Printing, placement, force validation, somewhere else, and why?
They should start with at least baseline measurements. And if they're going to start anywhere, they should start in the printer, because that's the largest number of opportunities in any process. And dialing in, understanding the capability performance of the printer and all the process parameters that go into that, environmental and materials. It's a lot of variables there that need to be checked and sussed out to get a good print process. So that's just based on sheer volume of opportunities. The print process is where to start.
Let's kind of go back to force settings for a moment. Force settings are often treated as simple set points. Why is force compliance a much more dynamic variable than many engineers realize?
Yep. So force is happening very quickly. If you think about the number of placements that are happening in a split second, I mean, we blink in about a quarter of a second, 250, 260 milliseconds. 20 components have been placed within the blink of an eye. So that head has to place it accurately, and it has to place it with correct force. And the force set points, yes, they're a set point and they should be met. And if they're not met, bad things can happen. Where one of the big issues is with force is the amount of energy dissipation that goes into the components during the placement. There's a very steep curve, so a very high force over a very short time can create a very steep impact. And that impact draws or displaces a lot of energy directly into the component when it's placed. And that displaced energy can create a microfracture. And that microfracture is still electrically active, still electrically intact and will get through its circuit test, and it will get through final test because it hasn't been thermally cycled. And when it gets into the field and it turns on and off and on and off in normal operation, that's when that crack is, or microfracture is going to propagate into a full crack. And then you've got a useless product that is being returned and people are upset.
Are these microcracks internal to the component so that it can't be viewed from the outside, or are they just so small AOI systems miss them?
The microfractures are certainly missed by AOI if they're small enough. Big enough, yes, they would be picked up. Could be picked up.
Right. So those are definitely latent defects. These are just little time bombs waiting to be exploited, right? It's like a crack in your asphalt. You know, you get a few winter seasons, and next thing you know, you've got a fault line there.
It's just a matter of time, right?
Yeah. How frequently should accuracy and force compliance be validated in high mix versus high volume environments? Is there a difference on the frequency based on the actual application, whether it's high mix or high volume?
I haven't been able to peg a difference between either environment, other than of all the customers we have measured over a year-on-year basis, that, again, 80-90% of those machines are failing when we go back to test them. So we know the frequency is less. The frequency, it's probably in the 6 to 8 month time frame. We have anomaly machines, like I mentioned earlier, that needed to be retested after 3 months. I mean, that situation could have been an operator who crashed the machine, who didn't tell anybody, who, didn't document it, and it produced a camera issue, which created some big offsets that were then triggered by the SPI system. But we know, based on collected data from clients, that even a 100 micron offset in the print process creates a lot of problems down the line. The defects and the DPM will go off the rails. So that's why regular measurement, more frequent measurement is necessary to keep machines in check.
I'm in the cleaning world, post-reflow cleaning world, as you know, and miniaturization is both our friend strategically as a business strategy and our challenge. Miniaturization has caused more assemblers to go back to cleaning because the tolerance for residue on highly dense miniaturized components is much lower than it used to be, back in the through-hole days and even early surface mount days. But it also creates a challenge, and it's more difficult to clean miniaturized components and bottom terminated components and things like that. In your world, how have things like UHDI and other examples of highly miniaturized, super high density assemblies and components and assemblies, how has that landed on your world and accuracy and reliability? And how much is it complicated and made what you do more challenging and more vital?
Sure. As components shrink, as technology tightens and tolerances tighten, we think about the thickness of a human hair, talking about 75 micron. Most specifications now are 1/3 of that, so 25 micron. So as Ultra HDI with their 12 mil or 12,000, whatever, I want to say it's so 12 and a half thou for lines and spacing. I mean, that stuff is getting to be very difficult to manufacture. And so that with all that, it becomes a zero tolerance policy for defects. You cannot touch a board with a soldering iron and expect the long-term reliability of that fix to be more than if it hadn't been touched. So it's zero tolerance, no defects, do it right the first time. Those are the things that need to be implemented with the future of our manufacturing.
What cultural or organizational barriers often prevent companies from adopting objective measurement practices? I'm sure there's I'm sure there's certain types of companies that are, maybe there's a little bit more wall. I'm sure there's types of management styles. How does that all play into your world?
It's also wide gamut. I would say there's the company or the electronics manufacturing service providers, EMS contract manufacturers. They weren't running more on tight margins, probably less willing to spend money on this type of this optimization exercise. Companies who aren't collecting data, so they're not collecting quality data. They don't understand DPMO. They're just manufacturing product. They're running blind in terms of measuring and understanding baselines and trying to improve. And those are some of the difficulties that we see with companies who don't understand the value of our service and what they get out of it. And so some of the cultural stuff, yes, could be the type of business it is. It could be ego-driven. They have engineers on staff. They have process guys who understand the equipment. Why do I need to spend any money on external stuff? So there could be a lot of different factors that are affecting why people don't understand. And education, that's maybe one of the others as well. I've been trying to educate the industry for 20 plus years, and there's still a boatload of opportunity with everybody and all these companies, and just trying to do a better job of that as well.
Talk to me about ROI in engaging in services like your company performs. Is it a straight line ROI? Is it a long-term, multi-year ROI? What's your clients experience some form of savings? How is that measured? How is that predicted? What kind of maybe claims would you feel comfortable making in advance on the subject of ROI?
Sure. It's the return on investment of anything you spend money on it's a calculation, and it's the bean counters who are helping the engineers run that calculation to understand whether they can buy a piece of capital equipment or service or whatever it might be. We have, to help ourselves, we've developed an ROI calculator based on inputs and the type of manufacturing is going on, the number of hours at each shift, and the number of lines and all that. The inputs that any engineering manager would know and can input to be able to understand what the cost of our service is and what they're going to get out of using our service. And just rough numbers, if you spend $20,000 or $25,000 on our service, you could expect to see that returned, the value of that service returned in ROI in about 9 months.
That's pretty impressive.
So it's good. I mean, it ends up meeting the frequency of measurement again. So there's this continual ROI on just doing the service. If you wanted to purchase equipment, the ROI is certainly less than 3 years, and that's based on price and everything else. ROI for a 3-year payback is, I think, decent for anybody willing to spend, capital equipment, money on capital equipment.
What advice would you give reliability engineers who want to proactively prevent defects instead of reacting to them?
So,
in our business, we tend to be both the arsonist and the firefighter, right? So we start all the fires we end up putting out. But at any rate.
Yep. So I think my advice would be to design the product and the process simultaneously, if you can, to make sure it's manufacturable with the equipment you have. I know it's not always possible, but that's where I think you get more for the whole situation. In terms of reliability, you're looking at all factors, and all those factors need to be considered. So implementing statistical process control is across the entire SMT factory. would be one thing to help do that, to understand what's going on. Implementing trackable KPIs so that you have some understanding of the metrics that you need to track to improve, to get better. Using the DMAIC principles: design, measure, analyze, improve, control, to do anything in your manufacturing operation. To baseline, to measure, to improve. And you need to measure. You need to use appropriate equipment for that measurement, and then be able to adjust and document all the process and the methods for the KPI calculations, so it's repeatable for anybody who steps into any role in that realm. And then lastly is to monitor your SPC, to verify all your actions, all your improvements, that they're working.
If someone were to be shopping for a company like yours, say the boss said, they went to the boss and said, yeah, we want to go to CeTaQ. And the boss says, no, get 5 other quotes, whatever the case. What kind of intelligent questions should a customer be asking companies like yourself to vet out the capabilities of the company and to make sure it's the most appropriate company for their specific need?
Okay, so you're suggesting somebody is wanting to buy equipment?
Well, let's stay with the services side. Someone's looking for a service provider that does what you do. What types of how would besides watching this podcast and go, oh, that's the one. Outside of this, how would someone validate your capabilities or other companies' capabilities? And what are the smart questions they should be asking?
They should be asking about gauge R&R capability of the measurement tools that they're using. That's often referred to as measurement uncertainty. Mm-hmm. There is a budget for measurement uncertainty, and that measurement uncertainty is essentially knowing how much error there is in the measurement system that we're using. So if they want to be educated, they should be asking about those things. They should be asking if the systems are traceable to a NIST standard. They should be asking about glass boards and their traceability. Are recalibrated? And do they have suitable gauge R&R factors for the process and or the machine? And what type of reporting comes out of the analysis when you purchase the service? So there's a couple of top hitters that anybody should be asking about.
So what kind of questions would you typically ask a potential client? Someone calls, they hear about your services. What's important for you to know, and what types of information should the customer be ready to provide you so that you can accurately provide them with some kind of expectation, both financial and outcome?
Usually when I'm on the phone with a prospective client, we're wanting to know what type of machines they're wanting to measure, how many of those machines, and what their goals are. Try to understand like their pain points, the reasoning for the service. Just try to figure out if there's other opportunities there as well. But with understanding the service, there's measurement project cost, there's labor, which is defined based on the number of measurements that we'll make, and then assessing expenses based on the travel to and from the time that we'll be there. So that's the simplicity of estimating a service event to help a customer. And in that process also, we try to provide that ROI calculator so they can understand what their payback might be in that service situation. So we try to make it as easy as possible.
And last question, if there's one takeaway you want my audience to remember about accuracy, force compliance, reliability, what would it be?
If you don't measure, you don't know. We'll start there and I'll end there. But and running blind is the worst situation imaginable. If you can measure, you have a baseline. You know where you are. You can begin to know how to improve from there, from that baseline. And product reliability encompasses so many variables that affect the product and a life of the product. So design for reliability, solder joints, interconnections, all this, materials and controlled handling, all these big factors are stuff that help the critical long life of any product.
In perhaps one of the most underrated statements, it's amazing what you see when you look, right? And
Sure.
And I think in this, for this conversation, knowing where to look, knowing where the skeletons are always buried is a good head start. For my audience that are watching this on our YouTube channel, if you want to get more information on CeTaQ Americas and get in touch with Michael, if you look down here where it says see more, all that information will be there. And if you're listening to this on your favorite podcast app, look at your podcast app and that information will be there as well. Michael, thank you so much. This has been insightful. I only asked you a fraction of the questions that I had prepared. But would it be okay if I got back with you and we can do a part 2 in this mini series of reliability and inspection?
Sure, absolutely.
All right. All right. You heard it here, folks. He's committed. It's a verbal contract. Are you going to be at Apex this year?
Yes, we'll be at Apex. Yep.
All right. Well, I'll look you up. Come and find me. And thank you so much for your generous donation of your time and your experience and your expertise. I really appreciate it. I'm sure my audience gets a lot of benefit out of conversations like this. Thanks for making this happen.
Of course. I appreciate the time. Thanks, Mike.
And that's a wrap on another episode of Reliability Matters. Thanks for hanging out. Whether you listened on your favorite podcast app or watched on YouTube, I really appreciate you being here. If you haven't already, hit that subscribe button so you don't miss future episodes. Are you on YouTube? A personal favor, give it a thumbs up and subscribe. Those 2 simple clicks really help us expand our reach. New shows drop every second and fourth Tuesday of the month, so mark your calendar. A big thanks to PCB Chat from the Printed Circuit Engineering Association at PCBchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Got a question or an idea for a future episode? I'd love to hear from you. Just shoot me an email at mike@reliabilitymatterspodcast.com. Want to learn more about this podcast? Head over to reliabilitymatterspodcast.com for that information. Thanks again for being here. Until next time, keep learning, keep doing it right, and remember, reliability matters. I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.